Hello, I welcome you all. The problem reads, determine the largest weight of the wedge that can be placed between the 8 pounds cylinder and the wall without upsetting equilibrium. The coefficient of static friction at A and C is mu S equal to zero point 0.5 and at B is mu prime S equal to zero point 0.6. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Benam. So we have been asked to determine the largest weight of the wedge that can be placed between the 8-pound cylinder shown and the wall. So we want to place this wedge so that it is in contact with the cylinder as well as the wall at C. And as we do that, we still want to maintain equilibrium, okay? In short, we do not want this particular cylinder to move, okay? We want it to remain the way it is. We don't want it to move either in the Y or in the X, or we do not want it to rotate, okay? Right. So what do we do? First and foremost, let's draw the free body diagram. Okay, we draw the free body diagram. So what I've done is I've separated the two pieces so that I indicate all the reaction forces. Right. So here we are. So let's start at point A. So we know that on the right of this cylinder, on the right, this is the right hand side, there is the wall, right? So, and also there is a cylinder that we are placing in between there, right? Remember? So we expect if this ball or this cylinder was to move, then it has to rotate clockwise like this, right? And by so doing, it means it's moving towards the left. And to counter that, we therefore need a friction force at point A here that we are calling Fa, right? And we also need a normal force. This is the reaction from the floor, okay, which is Na, right? So let me get rid of this. All right. What else do we have? We have the weight of the cylinder. We've been told that the weight of the cylinder is 8 pounds. Okay. Okay. At B, as we are placing this cylinder, as we are placing it between the wall and the cylinder, okay, we expect some reaction forces. Okay, some friction reaction forces in this direction, resisting the downward movements. All right, we expect this there. Okay, and we also expect this. Okay, so this is because this point here is C, this point here is B, so this is FC, this is FB, and then we also expect we also expect a normal force. Maybe I move this a little bit the other side so that I have some space. Okay, so like I said, this point is B. So as the wedge is being placed downwards, we expect these friction forces we are calling FB and FC and their respective normal forces. Okay, so this normal force is NB. This normal force coming from the point where the wedge is in contact with the cylinder. All right. This is mainly due to, of course, the weight of the wedge, and also we have this other normal force here, which is the reaction force also from the wall. Okay, so the wedge is exerting some force on the wall, and the wall therefore also reacts and produces this normal force. And in like manner also, we are going to have the same forces at B here. Okay, at B we have the same forces like so, but in the opposite direction. Okay, this is FB, the other one is NB. And we should remember about the laws that governs this normal force. Okay, so we know that this normal force here goes through the center of our cylinder, right? And even NA also goes through the center of the cylinder. All right. And then we have some angles that we need to mind. We do have some angles. So we know that this angle here is 30 degrees. Okay, and so is this angle here. Okay, is 30, and so is this angle here. All right, is 30 also. Okay, and so is this angle here is 30. All right, that angle there, it is 30 degrees. Right. So having said that, and having drawn our free body diagram, let's now, before we do the calculations, count the number of unknowns. So we have NA, we have NB, we have NC, then we have FA, we have FB, and then we have FC. Then we have, I forgot one more force, which is the weight of the wedge. I mean the weight of the wedge, this one here. So we have, this is what we are looking for. The wedge will have some weight, and we don't know what it is. Then we also have the weight of the wedge. So we have 7 unknowns. And how many equations do we have? For the equations of equilibrium, for the cylinder, we have 3 equations of equilibrium for the cylinder. For the wedge, we have only 2 equations of equilibrium. Summation of forces in the y and in the x. We cannot take moments on the cylinder because we do not have any dimensions. Right. And we don't even expect it to undergo any tipping or toppling over, right? But for cylinder, it is likely, there is potential for it to undergo rotations. Anyways, we have for the cylinder 3 equations of equilibrium, and then for the wedge we only have 2. So in total we have 5 equations of equilibrium. Therefore we need 2 more equations for us to solve these unknowns. So it means we have, for this particular problem, we are going to have 3 cases that we will need to test. Case 1 says we can assume that C, at point C there is impending motion. Therefore, Fc is equal to mu C NC, and we can also assume at B there is impending motion. Therefore, this becomes mu B NB. This is case 1. Case 2, we can assume that, like I said, we need 2 equations. So we need to try case by case. Okay. So we only have 3 possible combinations here, right? That we can get. Okay. Of course, the order doesn't matter, so we only have 3 possible combinations. Hence, we have 3 cases. And then the second case, so it doesn't matter how you add them up, okay? The second case is FA equal to mu A, that is, we are assuming at A there is impending motion, therefore we'll have FA equal to mu A NA, and we are also assuming at B there is impending motion, therefore FB equal to mu B NB. And then finally, we have case number 3. Okay. Case 3 is we are assuming that we have impending motion at A, therefore FA mu A, FA equal to mu A times NA, and we are also assuming that we have impending motion at C, therefore we have FC equal to mu C NC. Do we have any other combination? No, these are the only cases that are there because we only have 3 contact surfaces, A, B, and C. So if we are to combine the 3, then we'll have 3 possible cases if we are taking 2 at a time, right? Combining them in sets of 2s or in units, okay? So these are the 3 cases that we have that we need to try. So we'll try them once we also write down all the available equations of equilibrium. Then we'll be getting 2, okay, equations from each case. Then we try them, calculate W, check the slip at the other point, and do the same for the rest, and then pick out the largest W. Right. So then let's write down quickly the equations of equilibrium. All right, there we go. So we have summation of forces in the Y, like so. What do we have in the Y? We have NA, all right, minus 8 minus, all right, so for the reaction forces at B, they are going to have components because when you look at these, they are at an angle, so we need to get components of each one of them. I should have indicated them there, but space is not enough, so I'll just write them down in the equations. So we have NA minus 8. So I'm on the cylinder right now, summation of forces on the cylinder. So then there will be a component from NB, which will be a negative. Therefore, this is going to be equal to NB sine 30. Okay. Then FB also will have a negative, which is FB cos 30 equal to 0. Okay. Then we go to the wedge. The wedge, we have a minus W plus FC, okay, and then again the components of NB and FB also have components in the Y, and these are plus NB, okay, sine 30 plus FB cos 30. They are just the opposite, right? All right. So we are done with summation of forces for both the cylinder and the wedge. So we go to the summation of forces in the X, summation of forces in the X direction. Okay. What do we have? We have FA. We have FA minus, we are on the cylinder, FA minus components at B minus NB cos 30 plus FB sine 30 equal to 0. Then we have another one which is minus NC. This is on the wedge, minus NC plus NB cos 30 minus FB sine 30 equal to 0. Right. Then let's take moments now. We are going to take moments about this point I'm calling point O, the center of the cylinder. So I'll say summation of moments about point O equal to 0, anti-clockwise being our reference. What do we have? So we have FA times 0.5, okay, minus FB times 0.5 equal to 0. Therefore, our FA is equal to FB. Okay, so we have these equations. So what we need to do now is to try case by case. Let's go to case number 1. So FC is equal to mu C NC, and FB is equal to mu B NB. Alright, so using these equations, using this first case, we have all the equations now, which are 7, and we have 7 unknowns. So we know that FA is equal to FB, okay? So what we need to do, and we also know that FB, we just said FB is equal to mu B NB, okay? And therefore our FA will be equal to FB, which is equal to mu B NB. And then we have this equation under summation of forces in the X, okay, which is this one here, right? So this equation, if I was to bring it down here, I was to bring this equation down quickly. There we go. So if we are to replace this FB or FA here, so that it becomes mu B NB, and we did the same also, replaced FB here, okay, we replaced FB here, then we realize that once we've done our calculation, we'll find that NB will be equal to 0, FB will be equal to FA, which will be equal to 0, NC will be equal to 0, FC will be equal to 0, and NA, since FC is equal to 0, NA will be equal to NA will be equal to 8, right? NA will be equal to, okay, we had assumed what case 1, yes, NA will be equal to 8, okay, and then we have, therefore W itself will be equal to FC, which is equal to 0. Okay, so this is case number 1. Okay, you can check that and calculate. So we go to case number 2. Case number 2, we are saying we take FA equal to, we assume impending motion at A and B. So FA is equal to mu A NA, and FB is equal to mu B NB. So we are assuming impending motion at A and B. So the same equation, so we have FA, which is equal to FB, okay, which is equal to mu B NB. So we do the similar replacements. If we did the similar replacements, in this equation, okay, and then use the other equations later on. All right, we replace there, and we replace our FB there. We'll find that our NB will be equal to 0. All right, and our FA will be equal to FB, which will be equal to 0. Right? Of course, you are using other equations as well. This is just a Kickstarter. And then later on, you'll find that your NC from this equation here, your NC also will be equal to 0. Okay. Your NC is equal to 0. And therefore, your FC, therefore, you have your NA equal to 8. Therefore, you have your W equal to FC, which is equal to 0. Okay. Then case number 3, where we are assuming impending motion at A and C. So we have FA equal to mu A NA, and then we have FC equal to mu C NC. All right. So if we again using these two equations, we did our calculations using all the available equations, we are going to find that our FB, so we are using all the equations. I'll not show all the work that I was doing. I'll just give you the final solutions. You can do the calculations. So we find that if we did our calculation using case number 3, FA equal to mu A NA and FC equal to mu C NC, we are going to find that our NB is equal to 51.7128 pounds. Okay. All right. That's our NB. And then we'll find that our FA will be equal to FB, which will be equal to NC, which will be equal to 29.8564 pounds. Okay. Then we also find that our FC will be equal to 14.9282 pounds. Right? And then finally, we have W equal to W from this equation, the final equation, this one. Okay. W is equal to FC plus NB sine 30 plus FB cos 30. Okay, and if you replaced all the values, you find that your W is finally equal to 66.6410 pounds. So checking for sleep at since we assume that there is motion at A, impending motion at A and C, so let's check for sleep at B. If we did so, we'll find that our FB, okay, is equal to 29.8564 rounding off to 2 decimal places, 8.6 pounds. And then this is going to be less than the maximum friction at B, which is mu B times NB. And we know the friction at the friction coefficient at B. The friction coefficient at B, we've been told, is 0.6, right? Okay. So 0.6 times NB, NB is 51.7128. So if we did the multiplication 0.6 times NB, this gives us, NB is already there, 51 point. So if we did the multiplication, okay, we'll find that, so 0.6 times 51.7128, so we have a 31.02768, 31.03 pounds. So this therefore means no slip at B, which is okay, and hence our W, that case 3 gives us the right value of W, which is 66.64 pounds. Okay, so this is about it. This is the final solution. So this is the largest value, the largest weight that W will have without upsetting equilibrium, right? I hope the video was helpful, and if it was, give me a thumbs up, continue subscribing, sharing my channel, yeah, and many thanks for your support. Bye bye, and see you in my next screencast.